So again, we want to welcome everyone to tonight's webinar on Thundersnow. I am Joe Deli Carpini, the Science and Operations Officer, and with me tonight is Rodney Chai, one of our meteorologists, and as many of you know, one of our winter weather fanatics. So this is a good topic for him to help out on tonight. So first of all, I just want to say this is probably a little bit technical, so we don't want you to panic. This is a pretty complex topic, how thundersnow forms, but we're trying to keep it as simple as possible. But if you find this to be a little too confusing, please feel free to review our winter weather webinars on YouTube. Winter Weather 101, which kind of covers the basics, and then Winter Weather 202, which covers forecasting. But certainly feel free to drop me an email if you have any questions afterward. If you're really were lost or just kind of need me to break things down a little further, feel free to let me know, and we can certainly do that for you. So don't panic. So to start, we're just going to use a couple of definitions that we'll use kind of throughout the presentation. You may be familiar with the first one called frontogenesis. And all that is just a fancy word for lift caused by a difference in temperature. So almost like a front that's several thousand feet above the ground. We've talked about that in some of our winter storms, like around the 700 millibar level or 10,000 feet. But normally it's near cold fronts and warm fronts when we have lift caused by a difference in temperature, but it can also happen thousands of feet off the ground. So if we say frontogenesis, just think it's a fancy term for lift. Then there's a new one, which is called EPV. That's called equivalent potential vorticity, and don't let that scare you. But all that is doing is EPV is looking at instability in the atmosphere. And it's especially during the winter time when we don't have a lot of instability like we do in the summer. So it just is a term. It combines changes in temperature and changes in wind shear, but it's really just looking at instability. So the combination of the two, having the lift from frontogenesis and the instability from the EPV, are kind of our signals for getting thundersnow, and we'll describe that a little bit more. So to start, when we talk about instability, just to review, that typically when we think about thunderstorms, it's warm, moist air near the ground and colder air above. So this is known actually as upright convection. It's straight up and down since it's focused in the vertical. So these are our summertime thunderstorms. You're getting air that rises straight up, it cools and condenses, and forms showers and thunderstorms. So thundersnow is actually much different. There's still instability, but it's oriented in a different way. So to explain what we're talking about, we'll start talking about the different types of instability. There's the vertical instability that I just talked about. That's known as gravitational. So what you would think of is tossing a ball into the air, and if the air is unstable, the ball will just continue to rise. It won't fall back to Earth. And those are our updrafts that we talk about. So if you throw a ball into an updraft, it'll continue to rise until the air becomes stable. So this is what is really dominant in our summertime thunderstorms. So that's one type. Then we have something which is called inertial, and that's in the horizontal. So think about a marble rolling on a table. If the table isn't level, or maybe it has some dips or bumps or low spots, the marble is going to roll in that direction since it's not completely flat. And that's how the atmosphere kind of works. There are dips where it's cooler, kind of bumps where it's warmer. So the air can either sink or rise a little bit depending on kind of the distribution of temperature. So we have vertical and we have horizontal instability. And then there's one, this is the one that's important, it's called symmetric instability. And this is a combination of the two, gravitational and inertial. So think of it, it's a combination of vertical, straight up and down, and then horizontal, side to side. And this is what is most important for thundersnow. It's called symmetric instability. So the key point here is you can be stable in both the vertical and the horizontal, but you can be symmetrically unstable when the air is near or at saturation. So if you have an air mass that's at 100% humidity, for example, you can be symmetrically unstable, even if there's not a lot of instability vertically and horizontally. So think about it in the winter. We don't have 80-degree days and dew points in the 60s where we get these large instability values, or if you've been with us before, CAPE values. They're very low, minimal often, but there is instability in that kind of symmetric way. So during the wintertime, deep moisture is a key ingredient that must be in place. You cannot realize or utilize that instability if you don't have saturation. So that's one of the things we look at when forecasting. We look for frontogenesis, we look for the EPV, which is essentially this symmetric instability, and then we look to see that it's saturated, or you won't realize that instability. You can't use up that instability. So I hope that makes sense. So what I'm talking about here is called CSI, and no, it's not crime scene investigation. It's conditional symmetric instability. So in other words, having that symmetric instability, it's conditional upon having a saturated atmosphere. So again, without deep moisture, you can't have that instability that's needed for thundersnow. That's the thing that kind of helps release it into the atmosphere. And it makes sense during a winter storm, it's pretty much saturated. So you'll almost always have that taken care of for you. But that's the thing we're talking about, CSI. So, what does it look like? How do we look at that on a weather map? Well, again, we need this instability to be present in order for thundersnow to occur. So this is kind of a map of an idealized setting. It kind of shows the West Coast, but what we typically look for are these southerly winds aloft, which are increasing with speed with height. So you're going from weaker winds at lower levels to stronger winds at upper levels, and that's typical during the winter when you have a strong jet stream. Again, a saturated environment because you want to release that instability, and cold air to the west. You need some sort of temperature difference in order to generate, help generate the instability. So we'll look a little bit more at this. What does this look like? Well, on a diagram of an ideal winter storm, and this can be anywhere, the thundersnow is really prevalent kind of north and west of the center. So think about this area in shaded in red to the north of the warm front, and that's the ideal setting. So typically we have southerly winds aloft. Those are the black contours here. A saturated environment, certainly, and cold air to the west of the low, warm air is into the east. So we have all these things in place as long as it's kind of co-located, that frontogenesis, the lift above, or banding it's called, and having that instability, the conditional symmetric instability, then you can have thundersnow. It can also happen when you have a rapidly deepening storm too, but these are kind of the things that we look for when we forecast to anticipate if there's going to be thunder and lightning. So what this all means is called slantwise convection. So remember I talked about thunderstorms being upright convection, straight up and down. This is called slantwise, and there's a reason for that, which I'll show in a minute. So we have essentially cold air to the west of the system. We have the warmer air to the east. Remember, this is kind of the warm front, so your warm air is moving in more aloft. And this is the area where thundersnow is favored. You can kind of see this layer is slanted, so it's slantwise. The instability kind of rides up this way instead of straight up and down. And just to show, obviously this is different from what we see with the summertime thunderstorms. Again, upright convection, straight up and down, whereas here we're on more of an angle or slantwise. So the slantwise convection, it's sometimes associated with fronts, but it's often in what we call the comma head of the low pressure systems. If you look at a winter storm on satellite, you'll notice that nice comma head circulation. That's where the thundersnow is favored. So there are more banded clouds, banded precipitation, and that's where your thunder and lightning and the heavy snowfall rates are possible. It's not unusual with where you have thundersnow. You have so much instability that you can get snowfall rates of 2, 3, maybe even 4 inches per hour in some cases. So that's the area. That's called kind of the sweet spot for getting some of the heavy snow. So just to show another diagram of how this all works, obviously we have cold air throughout much of the atmosphere in a winter storm, but there's usually a little warmer air kind of moving in aloft with that, again, that warm front that's aloft. So at the top of the cloud, we have these negative electrons that are released from the water droplets colliding, and the negative electrons will sink to the bottom of the cloud. The positive ones rise to the top. So where you meet that warm air, you start to see a difference between positive electrons on the ground and negative electrons in the cloud here, and this is what causes the lightning bolt to form. Similar to summertime thunderstorms, except it's more elevated. So we're up, a few thousand feet. We're not down at the surface like we would be with thunderstorms during the summertime. So it all has to do with the difference in charge of electrons. Again, positive electrons near the surface of the Earth. You have an area of negative electrons near the middle. This could be 5,000, 10,000 feet up, usually associated with some sort of warm layer, but again, slantwise convection. So notice how the lift with these arrows starts low, it gets pushed up, but it's kind of slanted. It's not straight up and down like we would see in the summertime. So again, kind of a quick review on how we assess thunderstorm formation in winter storms. So just to scare you a little bit, yeah, there's definitely math with a purpose here. For those of us who went through college or any prospective students, this is why you learn all the math and all the calculus. But really what all this is to say is when we have negative EPV, remember I talked about that equivalent potential vorticity. When you have a negative value of that, it implies the presence of the CSI, the conditional symmetric instability. So when we look at a model forecast and we can see negative EPV, then we know we have that instability that's available to be released. And what I'm showing here on the right is kind of a cross section, and Rodney will get into a little bit more of this and actually show you what it looks like on radar. But what we're looking at here is your negative EPV here is in red. So this will be a model forecast that would show us, where is that negative EPV present? And then we're also looking at areas where these blue lines are kind of farther apart. And what that means is there's less of a change in temperature. That's called weak stability. You don't have true instability in the wintertime. You have weaker values of stability. So think about it going from a very, very stable air mass to one that's a little less stable. And that's all it takes to generate a little bit of instability in the wintertime. So in the shaded area, that's showing us where the two overlap. So we look for negative EPV on top of actually the frontogenesis area is what this is all showing. So that's the way we can diagnose, the potential for thundersnow with a strong winter storm. Now, the models don't always get the placement correct, but they at least tell us the potential. The location can be off a little bit, but at least gives us a little bit of a heads up. And a lot of these fields are actually available online. Some of the sites that we show, College of DuPage, for example, I believe you can look at these different fields. They're typically looking at about the 850 millibar or 700 millibar level. So you're talking, again, 5 to 10,000 feet roughly up in the atmosphere. So don't let this scare you. It's just a little way to explain how things kind of work in the atmosphere. So that's a brief introduction. What I'm going to do is have Rodney take us the rest of the way, and then he's also going to show some case studies, some brief case studies here from some recent events to show you, when we had thundersnow and kind of how it formed. And then this is a kind of one of our shorter presentations, but I want to leave plenty of time for questions, so we will do that. So Rodney, why don't you go ahead and take it from here, and then we'll do some questions at the end.
Thank you so much, Joe. So again here, it's kind of a similar diagram to what Joe showed previously, except this time around we actually put in the cities. So New York City, Hartford, Connecticut, and then Boston. So you can see what you can see here is that, again, the red line represent the area of negative EPV. So this, notice this range, this areas coincides with the blue lines that are kind of like, so if the numbers don't mean anything to you, just focus on how widely spaced they are from each other. So you can see 301, 303, 305. So they're kind of like spaced apart from each other. And so one way to think about it is, these are like areas of weakness in the atmosphere. So where the atmosphere is not as stable. So if you want to form storms, you need areas of relative instability. And as Joe mentioned, there's in wintertime, it's not like severe weather season where things are kind of magnified. You have a lot of CAPE, you have a lot of temperature differential, but in this case in winter, so we're dealing with things are kind of relatively less magnified than severe weather season, and this is where diagrams like this can really help you diagnose the atmosphere. So this is very generally speaking, but the moral of the story here is that you want to see where you have the the blue lines that are kind of spaced apart from each other, where it coincides with the negative EPB. That's an area where you have to be concerned for heavier snowfall rates and in this case convective snow. So, and in this case, it's lined up pretty much along the New York City to Boston corridor. So again, don't let this diagram scare you. It is actually a similar diagram to what was shown earlier, but in a different format. So in this case, instead of having different fields overlaid on each other, you have more of like a XY axis. So you have the vertical axis, the height of the atmosphere, and then the horizontal is the distance. So And where you see the areas of yellow shading, that's and kind of an area of basically CSI and your negative EPV. And so on the left-hand side, what you can see here is, so notice the dotted lines that is labeled momentum lines. So basically, when you advect, wind or airflow, over lines of different magnitude, in this case, the momentum gradient, you generate, instability. And again, very generically speaking, that's how you can get the upward rising motion of air and form storms. So hopefully that makes sense. But if not, you can feel free to put it in the chat box, and we can try to answer your questions. So this diagram here might be more familiar to more of you. So this is a typical winter storm, and you have the low pressure, the L, and so you have the cold front, warm front, and the purple line, that's the occluded front. Basically, it's where the colder air has caught up with the warm front. So that's, blue plus red give you purple. So that's your occluded front. And the area highlighted in shaded in red, that's your area of frontogenesis. And with FGen is really important for formation of winter storms and finding areas where you can heavier snowfall rates. And basically, it is a fancy term for, looking at where you have a temperature differential. And so, in a winter storm, again, giving you more of a, a real life kind of like case study. You have basically warmer air overrunning colder air. So the warmer air gets, because it's less dense, get pushed over the more dense colder air, and areas where they kind of interact with each other. That's your area of frontogenesis. And so the thundersnow again is favored in the area of frontogenesis, assuming your conditional stability is present. So in this case, so notice the frontogenesis that is surrounded by the like the cloud-like shape thing. That's your area of deformation. So basically, deform, I mean, if you think about it, it's where you have where you stretch the air mass a little bit, given the differences in wind speed and direction. So again, in general, in the atmosphere, you want to diagnose the atmosphere, you want to diagnose area of relative instability and areas where the wind field, the thermal field is different. That's how you get the gradient. And when things come together with enough moisture, you can get snow. So let's go through some case studies briefly. So this is 2005, December 2005. Some of you may remember this. So a rapidly intensifying storm produced 2 hours of blizzard conditions. So blizzard, again, its definition is you have at least 35 mile per hour sustained wind or frequent wind gusts over 3 hours, and then you have quarter mile visibility. Usually it doesn't mean, it doesn't need to be snowing a lot, but this kind of conditions can cause whiteout conditions, even with just, like a ground blizzard kind of things. So in addition to that, there's thundersnow along the I-95 corridor, and that coincided with evening rush hour. So that was just a recipe for disaster. And hurricane force wind gusts were observed in far southeast New England. So that you're talking about at least 74 miles per hour. And then the accumulation up to 1.5 feet northwest of the I-95 corridor. So you can see for yourself just how windy, up to 105 mile per hour wind gusts at Block Island, and over 100 miles per hour on the Outer Cape. So looking at the thermal profile, atmospheric profile, you can see for this event, you have a negative EPV as highlighted by the green and yellow color on the top left diagram. And then the top right diagram, you can see the area of white, that's area of strong frontogenesis, or the CSI. So when you put these two together, you can get a pretty explosive environment. And then at the bottom left corner, that's the area of strongest lift is co-located with the ideal snow growth zone. Typically, if you want nice dendrites that accumulate efficiently, you want the dendritic growth zone to be kind of around -10 to -18 Celsius. Now, for our coastal communities, like even including Boston, Cape Cod, and the islands, because of the of our proximity to the ocean, there's a lot of like salt nuclei in the atmosphere. And think of basically the salt particles suspended in the atmosphere as like areas that the water vapor can condense onto. So that's why we call it the salt nuclei. And when you get higher concentration of salt nuclei, that you can have the dendritic growth zone to be in a warmer temperature. So for example, like -6 to -8 Celsius is enough to form the dendrites for efficient snow accumulation. So it doesn't have to be -10 to -18 all the time if you are right by the ocean. And finally, you can talk about how explosive the environment is. You can have a lot of lift, but if you don't have moisture, you're not going to form anything. So, and sure enough, there was basically a deep layer of moisture. So fast forwarding to Christmas 2017, so you can see, you look at all these numbers, snowfall recorded in inches. I mean, that's nothing. I mean, it's just widespread 3 to 6 inches, except that most of this snow fell in about an hour. So you're talking about 3 to 5 inches per hour snowfall rate. That's pretty intense. And then on the right-hand side is a tweet by Judah Cohen. 3 inches of snow in the past hour in Newton with Thundersnow. So when you think of thunderstorms in the summer, those are the type of storms that can drop a lot of rain in a short period of time. So in winter, when you get thundersnow, you can drop a lot of snow in a short period of time. So this, again, the same case study. And so for those of you who remember this event, it was a rain changing over to heavy snow with thundersnow and brief blizzard conditions in the metro Boston area. And if you take a look, so there was a strong 850 millibar frontogenesis. So 850 millibar, that's, you're talking about 5,000 feet above sea level, overlaid with negative EPV. Those are the red lines. So basically you have an area that was favorable for thundersnow, and it was right over the Boston area. So it was a pretty loud morning on Christmas Day 2017 for Boston. And then and this was basically like a week later. I mean, January 4th, 2018. So this was a bomb cyclone, and there was, a bomb cyclone basically is defined as where the center of low pressure drops 24 millibar in 24 hours. So that's a rapid intensification of a storm system. And in this case, if you think about it, the faster a storm intensifies, the stronger the wind. So, you're going to have very strong wind, combine that with snow, you're going to have blizzard conditions. And then, on the bottom right corner, you can also see the coastal flooding as well, because the seas were being stirred up. So you can see on the visible satellite imagery, you can see that it's almost like an eye-like shape of the center of low pressure, just because it's so strong. and that was actually, I mean, all the way, kind of almost, you know, at the same latitude as the Carolinas, and you know, notice how just how strong the system is again. And on the right hand side, there was the same schematic that we showed you earlier. Just how, yeah, I mean, just look at how wide this system is, and you have all this, you know, lightning strikes, and you know, but this is January, so that's actually Thundersnow. So it's a very impressive system. So taking a look at 700 millibar, that's almost at 10,000 feet. So you have strong frontogenesis, that's the white colorings, and then the negative EPV, all those red lines. So you overlay them together, you have, again, strong frontogenesis, negative EPV, support heavy snow bands. And so we are talking about up to 10,000 feet. So there's a pretty deep layer of to work with. And taking a look at the surface reflectivity, you can kind of make out, okay, so you have that mid-level frontogenesis band kind of right over the Pioneer Valley into the Connecticut River Valley. And then closer to the coast, you have that coastal enhancement and thundersnow. So the coastal enhancement comes in the form of, you know, you're closer to the source of the moisture, and you also have, you know, your dendritic growth zone doesn't have to be at -10 to -18 Celsius. Again, it can be as warm as -6 because of the abundance of salt nuclei. And you know, combine that with the CSI and negative EPV, you can see those kind of like those flashes in the Providence area. So that's your thundersnow again. And then to the right-hand side, the dash line, that's kind of where your coastal front is. So right of that line, it's kind of rain or rain-snow mix, and then all snow west of the line. So in summary, so thundersnow develops in a completely different way from summertime thunderstorms. So you know, we emphasize slantwise convection, not vertical. Much less instability needed. You don't need like things like 3,000 to 5,000 joules of CAPE. Those are the kind of instability that leads to, you know, supercells in the right type of environment. You know, but you don't need that, and it forms in mesoscale bands. So there's a kind of like smaller scale bands, you know, and they might just be like 20 miles wide. So not too big, but enough to cause damage. And you need your convective conditional stability, CSI, and then you want to look for areas of frontogenesis and negative EPV. And the Storm Prediction Center meso-analysis page is a great site for it. College of DuPage website too. And last but not the least, you need to have moisture. So you do need to have ideally a deep layer of moisture to work with. Otherwise, you can have a very explosive environment, but it's not going to do anything. So I think before I'll pass it back to Joe at this time.
Okay, thanks, Rodney. So we'll go through some questions here, and we'll leave up the Jim Cantori stuff in the summary so everybody can watch him do his happy dance. All right, so let's see. And Rodney, you can help me answer these. Question from Kevin: does a closed upper low at 700 millibars lead to a blockbuster nor'easter that produces thundersnow and also causes frontogenesis at 850 millibars in this scenario? I can start. I mean, often, yeah, we want to see if you have a closed low aloft, that's definitely a stronger system. When we have 700 millibars, again, 10,000 feet, if it's not closed off, if it's open, that tends to be a system that's moving along quicker and doesn't have time to strengthen. So we like to see that for our stronger storms. That can also give you a better area of frontogenesis at that level. So yeah, definitely there's a greater potential for heavy snow and thunder snow if we have a closed off system at that level. Let's see. Question from Carrie. Question about the February 9th, 2017 snowstorm. And I'm going to have to remember this one. She recorded 17 episodes of thunder snow. How rare is this? And how does this storm compare to the blizzard of 78 in terms of thunder snow? Yeah, there's so many, Carrie, but yeah, I remember that one having a lot of thunder snow. The one that Rodney showed, the rush hour storm, was the most I could remember as far as thunder snow. It lasted, Rodney, it was almost 2 hours of thunder snow. I've never seen anything like that. Blizzard of 78, there was thunder snow. I don't know how much, I'm sure there was quite a bit, but we don't have obviously the folks to report it to us like we, would have had back then. I know it was reported at many of the airport stations. So that's kind of all we had back then, and some of the cooperative observers. But I'm not sure how that would have compared to the February 2017 snowstorm. But I remember that was another one that had quite a bit of thunder snow. So not something we really keep records on, unfortunately, just kind of more by our own observations. So unfortunately, I don't have any specific numbers for the blizzard of 78, but that certainly did have quite a bit. Another one from Kevin. Do the omega units play into a saturated environment along with deep moisture? So what omega means, Kevin, is it's just lift. So it's just a Greek symbol that we use for lift. So you obviously want that lift, you want the saturated environment, and you want to have the instability. So those are the three ingredients that you need for the thunder snow. All right, let's see. So from George, it appears that thunder snow appears when temperatures are in the high 20s or low 30s. My guess is thunder snow cannot occur when temperatures are in the teens or lower because of the lack of moisture and instability. In Minneapolis, never seen thunder snow in the dead of winter, but have seen it in our spring, March, and April storms when temps are close to freezing. That's interesting. And George is in Maple Grove, Minnesota. Thanks for joining us, George. Rodney, any comments on that? I believe I'm trying to remember. We've had thunder snow in some of the bigger. I've seen it here in colder environments, but I think it's probably a little bit more common in the when temperatures are just kind of below freezing. But I'll take your comments on that.
No, I think Joe, I think you are on the right track. And George, thank you for joining us from Minnesota. So my best guess is that, so George, you mentioned that you don't see thunder snow in Minnesota in the dead of winter, but you can see them, I mean, in March and April. And I think the reason for that, and probably connected to the East Coast thunder snow episodes. So in March and April, you start to get into early spring, and that's basically like the start of the severe weather season for the southern Great Plains and actually the central Great Plains as well. So so in a way, I mean, if you think about it, we emphasize the importance of having temperature differences, in the convective setup. So you have by March and April, you get the deep Gulf moisture to come into play. So you have a better chance of kind of like milder and more moist air being fed into just that cold, dry air mass from Canada. So you increase the potential of conditionally unstable environment for thunder snow to come into play. And as for the East Coast, I mean, I remember actually the January 3rd Mid-Atlantic storm, DC actually got thunder snow as well as Maryland. And on the East Coast, it's probably have to do a little bit of digging into this, but I'm pretty sure climatologically, the East Coast, just given its proximity to the eastern seaboard, the Atlantic Ocean, you get more moisture to come into play. And under the right setup, you can get, warmer air from all the way from Mexico, from the Caribbean. So, when you get this kind of distinction in air mass temperature, you just increase the potential for, again, an explosive environment. And under the right conditions with CSI, negative EPV, you can get thundersnow. So that's my best guess. Hopefully that makes sense.
Yeah, that's fine, Rodney. Thanks. Yeah, I think it definitely is more common here along the East Coast, just because we have a lot more explosive development. Now in the plains, you get that in the spring and the fall. That's when your stronger storm systems tend to come through. But it's a good observation. So we'll have to, it's something we'll have to maybe take a closer look at. Let's see. There was a question, I think, on the EPV. Yeah, from Ethan. We mentioned that negative EPV implies the presence of CSI, the instability. In what cases does the presence of negative EPV not actually correlate to a presence of CSI? It never. So in other words, when we have negative EPV, the instability is there. That's just, remember I showed that really complicated math equation. That's what that means. So if you have negative EPV, you do have the instability. So that's why we look at the negative EPV to kind of determine where the instability is. And then he had a follow-up question just on instability that I think would be worthwhile. We mentioned that less stable air can sometimes be all you need for just a little bit of instability. So what does that mean? So it means that we don't have, like Rodney said, true summertime instability. We don't have it's on a much lower scale in the wintertime. So we look at where areas are maybe weakly stable as opposed to truly unstable to kind of diagnose the instability. And he was asking, does this mean you're getting instability at the same level as the stable air? No, it's not. The less stable air is usually in a certain layer. Again, sometimes between about 5 and 10,000 feet or so is where we see that. But we're just looking for what's called weak stability. So instead of having values that are kind of off the charts, we're just looking for areas where it's just a little bit unstable. That's really all you need in that case. Question from Samuel: is Jim Cantori considered the king of thundersnow? Rodney, I would say probably yes. I mean, he's always out looking for it, as we see here. Has a webinar been done on storm bombogenesis? Rodney, remind me. I'm not sure if we've touched on that specifically. I know we've done some event reviews and case studies, but that's something maybe we can take a look at doing a little bit more. We did cover that a little bit, I think, in one of our marine weather webinars. But Samuel, we'll take a look at that, and if it's something we can throw together, we can certainly consider that for the future. Thank you. From Fred, December 9th, 2005, he was stuck on 128 from Waltham to Newton. Took 2 hours. Ugh. Yeah, I remember that day. That was not pretty. And let's see. Carrie wants to know, has ball lightning ever been reported with thundersnow? No, not that I'm aware of. Typically, it's in cloud or cloud to cloud. I don't think I've seen many cases of cloud to ground. Have you, Rodney? I think it's mostly within the cloud because it's not surface based.
Yeah, I think you're right, Joe.
Yeah. And then question from Mike: do reports of atmospheric turbulence as reported by pilots serve as a predictor of thundersnow? I suppose it could. And again, typically, they're usually not flying in that area because of the weather. But yeah, and again, this is on more of a slanted, air rising, not straight up and down. But yeah, I would assume there could be some turbulence in there, and if we did have some reports, we'd be aware that there's some strong lift going on in that area. So yeah, interesting question. All right, so that will wrap it up for our questions. Appreciate it. Hope this really wasn't too confusing for you. And again, you can review Winter Weather 101 or Winter Weather 202 for some of the basics. And then, of course, you can review this as well if you want to get a second look at some of that. And again, feel free to send me an email if you have any further questions, and I can certainly help you with that.